All right. Hello, everyone. Welcome back. So, last time we talked about some um, introductory problems regarding supervised learning. So, the problem was regarding the computational complexity. So, it was indeed something to really think about. Um, Usually, we tend to kind of ignore linear regression problem for being simple, right? Linear regression is indeed a simple problem where once you have a data matrix and once you know once you identify the regressor and the response variable, the later process is pretty simple. You just need to do some simple matrix algebra, and then as a result of that, you're gonna get a solution to your linear regression problem. So nothing really to think about because there's nothing mathematically complicated. But when it comes to a big data problem, the lesson from the last time was that even a linear regression problem, there can be a lot of challenge. And in fact, you need to really think through in terms of how you're going to implement a linear regression problem because it's not that simple. So today, what I would like to do is to introduce you briefly to what machine learning is, because I suppose a diverse background of the students who's taking this class. So we're gonna kind of brush up a little bit what you've learned from statistics course and some other machine learning courses before to get to talk about some real issues regarding linear regression of big data. Okay, so usually what people like to do is to classify machine learning problems into different classes. I think the most common case is a supervised learning, where you have not only data, but also have some labels associated with the data so that the labels can serve as a supervision to the machine learning problem. Supervised learning problems can further be classified into two different categories. One is a classification problem. The other is a regression problem. At the end of the day, they're mathematically the same problem. We can kind of generalize both of situations into the same mathematical equation. But classification problem is you have data and you want to literally classify that into uh, one of a few classes. So that's a classification problem. So you see, for example, in my case, image processing and computer vision is kind of my thing. So the most common classification problem there is image classification. So for a given image, you see some color values attached to each pixel, right? So each pixel has RGB values in a digital image. And by looking at those RGB values, what you want to do is to classify if the image is a dog or a cat or a car, boat, airplane, those kind of things. So that's a classification problem. Regression problem, on the other hand, is a problem where you're supposed to spit out some number. Okay, rather than a label, you want to come up with a number. So, for example, let's say you are interested in um, computing life expectancy from medical data. Okay, and let's say life expectancy is formulated as the number of years that a patient is expected to live, right? So in that case, the input is going to be some digitized medical data, and then the output is going to be some real number that indicates how many years that a patient is going to survive, right? So that's those are the two kinds of supervised learning problems. Unsupervised learning, on the other hand, does not have labels. So, unlikely to what I just, uh, you know, gave you as an example, unsupervised learning problems do not have any, output that is given as kind of a guidance for machine learning algorithm. So, the typical case of unsupervised learning is clustering. So clustering means you have a set of data and you want to discover some groupings of the data distribution. Okay. It may be that some of the data points are gathered around closely to compared to the others, and that kind of forms a cluster. And understanding if there exists a cluster or not kind of helps you understand the structure of the data, right? So that's a typical unsupervised learning problem. So we're gonna get to see both supervised learning and unsupervised learning for the rest of the semester. There are also some other categorical um, other categories for machine learning algorithms. Self-supervised learning is kind of hybrid in between supervised learning and unsupervised learning. Depending on the authors, people, sometimes consider self-supervised learning as a supervised learning problem. Some authors, on the other hand, likes to consider self-supervised learning as an unsupervised learning problem. But in my case, I prefer to give an extra clarity by giving an additional name in the category. So self-supervised learning is, so in case of supervised learning, you're given a data pair, x, y. So for a given x, you have a label y. And then what you want to do is to find the correlation between x and y in terms of, some machine learning model f, okay? In case of self-supervised learning, what happens usually is you're supervising the training of the machine learning model, for example, using the input value x itself, okay? So for example, there's this thing called an autoencoder, which is a neural network model that takes some image as an input, for example, and then spits out the same image as an output. Okay. So what's the point here? Well, we will have a chance to talk about it briefly later, but um, by doing this kind of self-guided supervised training, you can actually identify some underlying structure of the data distribution. So um, that's primarily the reason why people use self-supervised learning. But this is not going to be the main topic of this course. Okay, we'd rather focus on supervised learning and unsupervised learning mostly in this course. Um, there's also this topic of reinforcement learning. So this is kind of a different species. So if supervised learning, unsupervised learning, and self-supervised learning are all, some sort of analysis problem where you're interested in discovering some patterns in the data, reinforcement learning is a little bit different in a sense that we are interested in building an AI agent that can make actions, okay, to an environment, and then that environment will give a feedback to the agent that is making the action, and then the agent kind of modifies the action according to the feedback, and then through that interaction, the agent wants to achieve some goal. So I think one of the most popular example of reinforcement learning probably is AlphaGo. So I don't know if you guys heard about it. Go is Chinese chess, and it is basically like a chess game, okay? And AlphaGo was a reinforcement learning algorithm which was trained on thousands of Go games, and then after training, it was able to come up with its own kind of a strategy in terms of where to place the stone. And so the environment is the game of Go, and then the AI agent that is trained based on the reinforcement learning was able to come up with its own strategy that observe the environment, that looks at the current configuration of the stones, and then based on that, it can come up with an action, which is placing a stone, and then compete against the other human players. And in fact, AlphaGo was super successful and defeated all the human masters of Go. So that is one example of reinforcement learning. Again, in this class, we're not going to talk about reinforcement learning too much, but those are four categories that I usually categorize different machine learning algorithms. Okay. So what we're going to talk about today and the next couple of weeks is going to be supervised learning. Okay. Now, there are some basic assumptions we assume that the data is independent and identically distributed. So what that means is you have some distribution, okay, and then you're sampling your data from this distribution, okay. Now, when you do that, we are not going to impose any dependence between the variables. So for example, let's say we're analyzing the test scores of students. So we have math scores and English scores. And then the assumption here is that the math score does not influence the score of the English test, okay, and vice versa. And we also assume that the score distribution is similar to each other, so that at the end of the day, the original distribution of the math score and the English score is identical. So that's one assumption that we're going to introduce in order to make the discussion easier. But once we formulate this in IID data, then later on generalization is going to be pretty straightforward. So again, ordering of the data points doesn't matter under this assumption, because we're not gonna assume that the data points are not correlated, that they don't affect each other. And usually this assumption holds for many real world problems. So again, we're not imposing any anything. There's no stretch in terms of how we can generalize the real world problems into the theoretical setting. Of course, there are some exceptions. Time series one of those things. So let's say you have a temperature at day 0, and then you have a temperature at day 1. Obviously, you cannot say that the temperature at day 1 is independent of the temperature at day 0, right? It is quite likely that the temperature at day 1 is correlated with the temperature at day 0. So in case of time series, you cannot really assume that the distribution is IID, but other than time series, many of the cases, IID assumption is still effective. So given that, okay, this is kind of the formulation, okay? So here we're going to introduce some terminologies which you probably have already seen through previous statistics courses and things like that. But just to be sure and brush things up a little bit, let's say we have a problem, we have a machine learning problem where we have a variable x that describes the property of car, okay? So x may include here, it says x includes a price of the car and then engine power. So those are the two values, two parameters that describes a car. And then we have this thing called a hypothesis. Hypothesis, in other words, is kind of a mathematical equation which takes x as an input and then returns something, okay? And we just don't want, we don't want to have just a random function. We want that function to have some agreement with what we know about the cars. Here, we want to classify cars into binary classes. Is it a family car or not? Okay. So we want the function, we want our hypothesis h to return 1 if x is a family car. We want the hypothesis h to return 0 if x is not a family car. So that's how we're going to formulate this binary classification problem. Now, a few additional terminologies that we're going to introduce, okay? Well, here in this figure, instead of 1 or 0, we're using, well, actually, it's 1 or 0. So again, so the data set X over here is comprised of pairs of data. So T is the index of the data point. So we have N samples in our data set, and each of the sample is basically comprised of X and R, where R is defined as either 1 or 0. 1 means a family car, 0 means not a family car, and then X is is the price of the car, and then the engine power. So let's consider this hypothetical example where we have a plot of different data samples. Um, Dots indicate the price and the engine power of that corresponding car. And then the dots are either with the negative sign or the positive sign. So the positive signs are family cars, and then negative signs are non-family cars. Okay. Now, with that, what we would like to have is a hypothesis, some mathematical function that can give us the number of 1 if um, a car is a family car, and then 0 if it is not a family car. And a simple mathematical function can be this if and else condition here, right? So we're defining our hypothesis H, okay, which is a mathematical function, as sort of an if and else statement. So if price is in between some price P1 and some price P2, and if and the engine power is between some engine power value E1 and some engine power value E2, then we're going to consider that car as a family car. Otherwise, we're going to consider it as a non-family car. So that's one possible hypothesis. And then, in fact, the function, the hypothesis H, is illustrated in this figure over here. So the shaded area is what where the values satisfy being a family car, and then the other area is a non-family car, according to this hypothesis H, right? So if we parameterize, okay, so H is our model then, that's our hypothesis. And then P1, P2, E1, and E2, those are the kind of the threshold values, right? And in a statistical term, these are called the model parameters, okay? Model parameters. Now, given this hypothesis and then model parameters, depending on how you choose model parameters, there can be many different hypotheses. There can be infinitely many different hypotheses, because there's infinitely many combinations in terms of how you choose those parameters, right? So among those infinitely many choices of hypotheses, which we call capital H over here, okay? So capital H is a set of those infinitely many choices of hypotheses, okay? The ones that are between this tight box over here, which we're going to call S, and then this box over here, which we're going to call G, okay? So S is probably the tightest hypothesis among this set H, right? Tightest in a sense that, if you look at the data samples, the positive signs are tightly enveloped within the hypothesis A, S, right? And G is kind of the most kind of generous or most kind of loose hypothesis, right, in terms of how it envelopes the positive signs. So G is the most general hypothesis, and S is the tightest and the most specific hypothesis. And anything in between the two, anything in between S and G, which is the gray rectangle over here, is called a consistent hypothesis, okay? And then a set of all the consistent hypotheses are called a version space, okay? So those are the terms that you probably want to brush up a little bit before we get into the later topics. So here we have definitions of consistent hypothesis. A hypothesis H is consistent with a set of training examples X if and only if this holds true, meaning that if you have a consistent hypothesis, your prediction accuracy is going to be 100%, right? That's the definition of consistent hypothesis. The version space is basically the set of all consistent hypotheses, okay? Set of all machine learning models that has 100% accuracy. So that's what is called the version space, okay? Now, Based on that, we can also define an error of hypothesis. So the error is simply in the binary classification problem, we can define it as how many times we miss, right, out of those n data samples. So um, this annotation here is a little bit weird, but what it basically says, uh, we're gonna, whenever we misclassify a car, we're gonna add it up. Okay, we're gonna count that, and then at the end of the day, we're gonna divide it by the total number of data samples. So at the end, this equation is going to give you the percentage error, right? And that's one way of defining error of hypothesis in this binary classification problem. Of course, there can be many different ways of defining errors. And in fact, we're going to talk about later things like distance metrics, which are quite important because the way that you've defined error can affect the performance of the trained model and then the training procedure. Okay? But at the end of the day, error of hypothesis is defined as a mathematical function that gives a measure of how wrong your hypothesis is. Okay. So from this family cars example, we introduce some of the basic notions, right? First of all, the terminology hypothesis is something we're going to use frequently. So this is, in a loose sense, is equivalent to a machine learning model. Okay, so we must choose some machine learning model to be able to predict something. Okay, so that's first bullet point. The second thing is we may have inductive bias. So inductive bias is another term that we're going to see often throughout the course. Which basically says the choice of your hypothesis will affect your result. So for example, this is the inductive bias that we introduce over here. We assume that the machine learning model has to look like a rectangle here, okay? And because of that, there is certain limitations in terms of how we can classify given data distribution. In this particular example, the rectangular model works just fine. But in case, let's say you have some negative signs over here and then positive signs over here, then what are you going to do, right? And because of that limitations of the shape of the machine learning model, you are not going to be able to classify these cases correctly. Right? There's no way to draw a rectangle that can completely separate positive signs and negative signs. So that's what is called the inductive bias. Inductive bias is an inherent problem that exists in the choice of machine learning model. And because of that, there's going to be certain trend or limitations in terms of what kind of result you can get. Another thing is all consistent hypotheses. So all the machine learning models that are accurate can be found between most general and most specific hypotheses. And that's called a version space, right? So that's another thing that we just saw. And then finally, in practical applications, there may not be a consistent hypothesis. Again, like the example that I just gave you, there may not be a consistent hypothesis due to the distribution of the data as well as the shape of the hypothesis space itself. So the inductive bias plays an important role here. Okay. So again, this is probably more or less how the real world problem would look like. Okay. We can safely say that there's no problem in real world which you can use just a simple rectangle to classify everything. Rather, the hypothesis space is going to be the geometry of the machine learning model is going to be way much more complicated than just a simple rectangle. That might be due to noise in the data set. Obviously, if you have many, lots of noise, then the distribution of data is going to be way more complicated. So noise is one factor. Other factor is, data representation itself might be already a little too complicated. So for those, for that kind of reasons, we need to have, we need to find some trade-off between the complexity of the model and, well, we need to define enoughly complex model, right? So, if you use a simpler machine learning model, then obviously it's simple to formulate, so it doesn't exceed your, brain capacity. That's the first thing. And then if you have a simpler model, then obviously it's easier to train and easier to explain. So obviously, if you think about it, an equation, a mathematical equation to describe this potato shape over here, this ugly potato, versus a mathematical equation that describes this rectangle, if you think about the number of parameters that is required to do so, is going to be significantly different. In case of rectangle, we just saw that only 4 parameters will be sufficient. Whereas if you want to describe this free-form shape, you're probably going to need way much more than just 4, right? And the fact that you have more parameters means that you have more numbers to figure out. Therefore, it is more difficult to train. Because of the same reason, if you have only 4 parameters, then the intuitive meaning of those parameters are kind of straightforward, right? So for example, P1 is the lower bound of the car price. P2 is the upper bound of the car price, and it's very easy to explain, very straightforward. But in case you have a large set of parameters, then obviously it's going to be way much more difficult to explain what those parameters are. And lastly, and this is another important part, simpler models generalize better. So for example, if you have a linear model, then you can easily extrapolate the trend of data. Versus, let's say you have some higher order model that looks like this. Then the extrapolation of this result can be quite different according to, who actually extrapolates, the model trend. So simpler models are often preferred as far as they provide a similar accuracy. Okay, so that's kind of, first rule of thumb. And especially, I would like to emphasize this because, nowadays the trend is just apply deep learning on everything, right? Just bring a deep neural network with millions of parameters and then just, train it. If it doesn't work, just increase the number of layers, increase the number of neurons, and, you should be good to go. I mean, that seems to be kind of the trend because of the hype of deep learning and, AI. But as a matter of fact, that's actually not a good strategy. You need to come up with a simpler model. And that's especially true in the context of big data. Because you have a large amount of data, you don't want to make your problem too complicated. Okay, so we're going to talk about those things throughout this semester. Now, a few more words about noise and model complexity before to jump onto the real topic. Errors in measurements of input attributes or class labels can cause noise, obviously, right? So the main cause of so what it says is basically when you measure inputs or when you measure the classes, there might be some noise introduced by that. So for example, medical imaging, let's consider that. Okay, in order to generate class labels, what needs to happen is some medical expert has to take a look at a medical image and classify if this image contains a certain type of disease. But as you know, even the expert, humans are not perfect. So sometimes even experts make mistakes, and then they may come with labels that are not true. And that's one of the popular causes of noise in medical imaging applications. There can also be input noise. For example, the imaging device itself, may contain some noise. So this is an X-ray camera, right? And then when you take an image of a person, the device itself may contain some noise characteristics. So it may not be an exact, precise representation of the real physical thing. Plus, there can also be an error caused by the compression of the image, okay, or the resolution of the X-ray device may not be enough, so that some of the detailed features are just smudged out. So those are very common sources of error, or the input noises. In social science, for another example, people oftentimes report some false values, either willingly or unwillingly. So, for example, let's say you're doing a demographic survey, okay? And when you ask the height of a person, okay, people do have a tendency to kind of exaggerate their height, okay? So, because of that false report, your demographics data may contain some error in terms of person's height, or it may just that the person does not is not aware of his or her actual height, right? In that case, the person, even if she was not intended, she didn't intend, um, you know, we may see a false value in our data set. So those are all kind of measurement error or report errors included in the data set. Also, there can be some unknown or ignored attributes. Okay, so let's say you're interested in monitoring the ticket price of airplane trips, and you've been measuring the number of people who are traveling to that destination, maybe the season of the day, or so you have included some parameters. But then there might be some other factors that are not included in your parameter selection, or the factors that cannot be measured in a practical manner. Let's say, there is an event in Iowa City, for example, which caused a temporary increase of, plane ticket demand, and therefore increase in plane ticket price. That kind of cause is really hard to measure, right? So because of those unknown or ignored attributes, there is a great chance that your data may contain some noise, okay, that is not modeled properly into your hypothesis. And finally, this is kind of an inductive bias thing. So, when your model selection is wrong, obviously, then you will not be able to obtain any accurate result. So those are kind of common causes of noise. Okay. So far we've talked about some of the basics of statistical learning. Okay, we talk about we define some of the terminologies that are crucial. Okay, I believe you've seen that from other statistics courses, but it's good to kind of brush up those concepts a little bit. Now, the main topic that we're going to discuss is the regression problem. So what we're going to do is to talk about the regression problem, especially linear regression, and then we're going to start thinking about some of the practical issues regarding applying regression analysis to a large amount of data. So the reason why we're going to talk about regression is because classification, in some sense, is a regression problem. We're going to see that in a second. The regression problem is basically you have some attributes that are given as an input, and we assume that it contains noise. And what you want to do is to predict the real number. So mathematically speaking, this is how your data look like. And what you want to do is to come up with this mathematical function G, or hypothesis, that takes in, a set of attributes as an input, and then spits out a real number that corresponds to the real number that's associated with the data point T. Okay. In case of classification problem, R simply becomes a natural number. So instead of a real number here, in case of a classification problem, you can simply formulate a classification problem by setting R equals to a natural number n. Or sometimes, more preferred trick is to represent it as kind of a binary encoding. So let's say you have image classification problem where you want to classify animals. So cat, dog, horse, let's say, right? So in that case, you can formulate your problem by putting the labels as a combination of the binary values. So in this case, you're basically turning on and off the switch. So in case you have 0, 1, 0, then that means this particular set of attributes belongs to those of dogs. In case you have 1, 0, 0, it's a cat. Or in case you have 0, 0, 1, it's a horse. Okay. So this is called a dummy variable representation or one-hot encoding. There are actually many names to it, but this is kind of common trick, okay, that you can apply to classification problems. And again, at the end of the day, it's pretty much the same, right? So you just switch this real number condition into that dummy variable representation, then mathematically you have exactly the same problem over there. So that's why we're going to talk about mostly regression problem. Now, at the end of the day, we want to minimize some error, okay? In this case, we're going to use a quadratic error. So the quadratic error is typically defined as like this. So RT is the true number, the true value, the ground truth value associated with the teeth data sample. And then G is our prediction model, and XT is the input attributes. So what is predicted from the attribute XT must be as close as possible to the ground truth RT, and that's what the quadratic error function says, okay? So that's typically how people formulate regression problems. So, okay, so let's consider something a little more tangible. So one of the simplest case you can think of is linear regressor. So let's say you have some variable x, okay? And for simplicity, let's just consider it as a single variable, okay? So let's say by using the price of the car, let's say you want to classify if the car is a family car or not, right? So then x is a variable concerning the price of the car. And then, the linear model, linear hypothesis that you're going to have is W0 plus W1 times X. So W0 is the y-intercept, right? And then W1 is the slope of the curve. So you're basically defining a linear function, right? Where this is W0 and then the slope is W1, right? Now, if this is your model, then the quadratic error is represented like this, okay? I just substituted this linear equation into that quadratic error function in the previous slide, okay? And what you would like to do is for a given data set that's available to you. So let's say you have n data samples. For those n data samples, you want to minimize the discrepancy between the ground truth value and the model prediction, the prediction from the linear regressor. That's what you want to do, okay? And you can use simple calculus to find the minimal solution to this, right? I'm not going to do everything, but, just to help you brush up a little bit, if the error function is defined as, capital E, then the derivative of that error function with respect to x at the optimal value has to be what? Has to be 0, right? So you learned this from calculus. When the slope is 0, what that means is you have, let's say, some function e like this. These are the points where slopes are 0. And if the slope is 0, that means it's either local minima or local maxima. right? And then another condition is, in order to make it a local minima, what you want to do is to make sure that the second order derivative is what? Is bigger than 0. Okay, so if the second order derivative is bigger than 0, that means the shape of the curve is like this. If it is negative, then the shape of the curve is like this. So in case this is negative, then you're at a maxima. In case that this is positive, then you're at a minima. Okay. In case of the quadratic error, obviously the second order derivative is bigger than 0 all the time. So you will not have to worry about this situation. Okay. So that's kind of a mathematical background. And skipping all the detailed derivation, you will reach to this analytic solution if you solve that dEdx equals to 0, and dEdx, sorry, the second derivative is bigger than 0. If you solve this two conditions, then this is going to be the solution that you're going to get. So in case of a linear regression problem, you have an analytic solution. Analytic means you have a solution that you can derive by your hand without doing numerical calculation, which is pretty good. What that means is you just plug in your data set into this formula and then compute W1. And same thing. By using the result of W1, you plug that in, you plug the the numbers into this X bar and R bar, which is simply just the average of the values, and you have W0. Okay. So in case of linear regression problem, you can derive a solution pretty easily. Okay. Of course, you have if you have more than just one variable. So let's say now you have D variables. Okay. So D is the dimension of the parameter. And in case you have a multi-variable situation, then obviously you need to introduce multivariate calculus. So in that scenario, what we're going to do is to use a matrix representation. So since we have n data samples, okay, by constructing a data table, we can have a matrix that looks like this. And this matrix is exactly like those Spark data frames, right? So each of the row is an entry, okay? So in case of baseball data set, each of the row is a baseball player, right? And then each of the columns is either a salary or number of hits, number of home runs, those kind of things. R, on the other hand, is a collection of simply, the values, the response variables. So it's simply just n by 1 dimensional vector. It's a column vector. Okay. Now, under this representation, what you have is this linear model in the matrix representation. So we have R, which is an n by 1 matrix, X, which is n by D matrix. And from that information, we can infer the dimension of the matrix W, right? In order to have n by 1, the matrix dimension on the left-hand side and the matrix dimension on the right-hand side has to be compatible, right? So in order to convert this n by D matrix into n by 1, you need to have D by 1 matrix. And obviously this y-intercept, right, B, has to be n by 1 to match the dimensionality. Okay, so that's our representation of the linear model. Okay, and those two, W and B, which is a D by 1 matrix, and then it's actually n by 1 matrix, those are called the model parameters. Okay. And what usually happens is we just repeat. So in case of B, this is an n by 1 matrix, right? Usually what happens is we repeat the same value for all n entries, okay? So which is called the broadcasting. So by convention, B is a scalar number, okay? That's why It said B belongs to a real number, B is a scalar number, right? But in fact, to be rigorous, B has to be an n by 1 matrix that has a repeated entry. Okay. Now, this B thing is a little bit annoying because matrices are, usually easier to handle for multiplication operations. But when you have additions, it is kind of, tricky. So in order to make the problem even simpler, we're going to apply a trick, which is to convert x into x1. So we augment the data matrix X with additional column, which is comprised of ones. So again, if this was data matrix X, we just add a new column that is comprised of a bunch of ones. Okay. That's one thing we're going to do. The other thing we're going to do is we're going to define a variable called theta, which is simply just an augmentation of W with the value B. So again, if this was a W matrix, what we're going to do is to basically add additional row that is comprised of a bunch of B's. The reason why we're doing that is because obviously, if you convert it in this way, then this one over here is simply just x1, and then theta over here is WB. And if you multiply them together, you will see that it becomes xw plus b, which is the original equation that we had, right? But then the benefit of this formulation is that we only have a multiplication. So now we can simply just multiply the inverse of x in order to calculate the unknown theta. Okay. Now here's the real deal. X is what? It's an m by d matrix. Well, in this case, since we augmented, one dimension, it's n by d plus 1 matrix. Now there's a good chance, right, that n is not the same as d plus 1. Usually in big data problems, n is much higher than d plus 1, right? You have thousands of baseball players. You have a few hundreds of baseball statistics, right? So in that case, n is much larger. Nonetheless, it's not a square matrix. Matrix inverse can only be calculated when the matrix is square matrix. But in this case, we have a matrix that is super tall. We have large n, and then we have some d. So how do you compute the inverse? Well, we can apply some tricks, okay? So I basically just swapped the left-hand side with the right-hand side. So x theta equals to r equals to x theta, same thing. Now, what I'm going to do is to multiply x transpose to both sides. So it becomes x transpose x times theta equals to x transpose times r. Okay. Now here I'm going to apply a wild assumption. Okay. X transpose x, which is d by n times n by d. And as a result of that, x transpose x is a d by d matrix. Right? So it's a square matrix. And we're going to just assume, okay, without further explanation, we're going to just assume that d by d matrix over here has an inverse. If x transpose x has an inverse, what's going to happen is then we will be able to multiply the inverse of x transpose x on both sides. And that will give you this equation over here. So we simply just multiply the x transpose x inverse on each side. Now we have x transpose x inverse times x transpose x. So inverse times matrix itself equals identity. So this whole thing becomes the identity matrix I. So I times theta is just theta because it's the identity matrix. And therefore, we derive this conclusion. Okay, theta equals to x transpose x inverse times x transpose times r. Okay, which is, by the way, the very equation that we discussed last time on Tuesday. Now, long story short, here's kind of conclusion. When you have this linear system of equation where X is n by d matrix with n greater than d, okay? I'm just omitting d plus 1 here, okay? So when n is greater than d, then the solution to this, remember x and r, those are known values from the data set. Theta is the unknown. So the solution to this linear regression problem is theta equals to x transpose x inverse times x transpose times r. So if you look at this matrix over here, okay, this entire thing works like as if it's a inverse of x. Okay, so you can define this to be, let's say, x plus, and the equation becomes theta equals to x plus, I mean, not literally, matrix addition, but just a superscript, right? So theta equals to x plus r. So this is, quite similar looking to x inverse r, okay? But it's not exactly x inverse. So this thing is called a pseudo inverse. And the mathematicians who kind of discovered this was Moore and Penrose. So it's called the Moore-Penrose pseudo inverse, or simply just, pseudo inverse. So the conclusion here is that the solution to linear regression problem is simply just a pseudo inverse times the y-intercept. And that's basically it, okay? So again, even for the multivariate cases, linear regression problem has a analytic solution, which you can easily compute, okay? Which is nice. So here's how linear regression can be used, okay? Here I'm gonna show you some toy example. The toy example is based on a simulated data set. So we artificially generated 100 data points by using the sine function. So sine pi of x is the ground truth. That's the precise trend behind the data set, okay? Obviously, we will pretend we don't know what the answer is, but that's the right answer that we're looking for. But then what we're gonna do is, to make it a little bit complicated, we're gonna add the Gaussian random noise. So as a result of that, the red dots over here in this figure, those are the data points that are generated from this simulated data set. Now, what we're gonna pretend is that out of those 100 data points, we have 7 data points, only 7, okay, data points that's available as training data. And those are indicated by those black dots. So using those black dots, what we're gonna do is to train a linear regression problem. And a few slides ago, we saw the formula for linear regression problem. And by just simply putting the values into that formula, this is going to be the optimal solution you're going to obtain. And that looks exactly like this black line over here. Okay. So obviously, in case of training data, we have pretty small error value, because that black line over there is actually a good estimation of how the training data is distributed. But if you compute the error on the test data set, so the red dots that are not included in the training of the model, okay, if you apply the trained model G to those test data set, the error that you're going to achieve is around 0.21, which is way higher than the error value on the training data. Okay. Now, Obviously, in this case, you would probably want to have a model that is more complicated than a linear model. This is a good indication. The fact that the training error is much lower than the test error is a good indication that your model is probably too simple. Okay. So in case you want to have more complexity, you can use this trick, okay, which is called the basis function trick, and then make your model a little more complicated. So we can generalize linear regression using basis function and make it into a nonlinear regression problem. The way to do that is by introducing this basis function phi. So instead of representing gx as sigma of wi xi, we're putting another layer here, which is the basis function phi, and then represent the response variables in terms of the weighted combination of the basis functions. Okay, so in case when phi equals to just x, right, then this equation is going to become exactly the linear equation. When phi is, something other than x, let's say, x squared, then you're going to have a quadratic regression problem. Okay, so a common choice, in fact, is a polynomial basis, because polynomials are, easy to handle compared to like other complicated functions like exponentials or logarithms and things like that. But people do use other type of functions. But polynomial is probably the simplest choice for the basis functions. Now, without explaining too much, here's kind of how exactly you can apply this basis function trick. So R is still is a n by 1 vector, okay? And then W is going to be a matrix that is about the same form. So here, I'm going to just rewrite the equation. So R equals to x theta was the form that we have looked in a couple of slides ago. So R is going to be just same as what we had before, and then theta is still the unknown that we're interested in finding. Now, what we're going to do with x is actually to use the basis function. So previously, we just typed in x11, x12, x13. So that's the first data sample. x21, x22, x23. Those are second data sample, and so on and so forth, right? So all the way up to xn1, xn2, xn3, and so on, right? That's how we formulated in the linear regression case. You can actually convert this into something more sophisticated by using the basis function. So you can actually, for example, add, let's say, on top of x11, you can have x11 square, and then x12, x12 square, x13, x13 square. Same thing, x21, x21 square, x22, x22 square, and so on and so forth. So if you add the columns for squares, okay, and try to solve this equation, then in effect, what happens is you're solving for a model that looks, a model that looks like this. Okay. If you think about the geometry of the matrix, this is kind of the formulation that you're solving for, which is a quadratic equation now. Okay. So still, if you look at the matrix level, this is still a linear regression problem. You can still compute theta by computing the pseudo inverse of x and then multiply that to r, right? But the way that we formulated x is a little bit different. We now added the quadratic term, right? And as a result of that, you can convert your model into a quadratic model, okay? But still the solution is r equals to, theta equals to the pseudo inverse. So X transpose X inverse times X transpose times R. Okay. So this is kind of a trick that people use to make a simple linear regression problem into, polynomial regression problem or some other arbitrary function representations. Okay. Now, in case you have polynomial regressors, when you have a, let's say, degree 0 polynomial, degree 0 polynomial is just a constant. So obviously it's just the horizontal line, and still the black dots are the training data set, and this horizontal line is the one that fits, well to the black dots. But obviously this does not represent the true trend of the data set. If you have a degree 1 polynomial, that's exactly the same as a linear regression problem, which is W0 plus W1 times X. Okay. And if you increase the degree of the polynomial, now we have W0 plus W1 times X plus W2 times X squared. And as a result of that, you have a smooth curve like this that gives you a better fit of the trend of the data set. So presumably it's going to have a lesser error. If you increase the degree into 3, then you start to see a curve that aligns pretty well with the original sine curve, right? So degree 3 polynomial is W0 plus W1x plus W2x squared plus W3x cubed, right? So that's degree 3 polynomial. And by solving that, you can have something very close to the ground truth. Now, if you keep increasing the degree, when you have degree 4 polynomial, you start to see some, departure of the model from the ground truth, okay? So if you look at this area and this area, obviously the discrepancy between the model prediction, which is the black line, and the ground truth value, which are the red dots, are quite severe. But the reason why we converge to that kind of model is because we use only those 7 black dots as training example. And from the perspective of this black line, we don't really care other than those black dots. So as far as the black curve here goes close to the black dots, we don't really care about the rest of the red dots here. And that's why we start to have this kind of a departure from the ground truth. And then keep increasing the degree, right? So now we have degree 5 polynomial, and then finally we have degree 6 polynomial. And in case we have degree 6 polynomial, we have a perfect training accuracy. If you look at the curve passes through all the black dots, which means as far as those black dots go, our model is a perfect predictor. And the reason is because we have 7 training data points, and we have degree 6 polynomial. And if you think about it, we have 7 unknowns, right? W0 plus W1x plus W2x squared, all the way up to W6 x to the 6. So if you count the unknowns, we have W0, W1, W2, W3, 4, 5, 6. That's total 7 unknowns. So 7 unknown, 7 data samples. So we can define an exact solution, right? So the error for training data set in this case is 0. Although the error for test data set is way bigger than 0, right? So in fact, this is a kind of a table that compares the different degrees of polynomial in a quantitative manner. So as you can see, the training error goes down as we increase the degree k, right? So in case k equal to 0 model, we have 0.58 training error. As we increase the degree of the polynomial, we can see that it converges towards 0. However, if you look at the test data set, originally the error was pretty similar, and then it kind of goes down together with the training error, but then after k equals to 3, it kind of goes up again. Okay. So from there, we know that k equals to 3. So the degree 3 polynomial is the best regressor for our problem. Okay. So this is kind of an important lesson. In case of neural network, effectively, you have k equals to several millions. Okay. So you have to be really careful, right? If you have k equal to several million, then for training data, you can almost always have a perfect fit, meaning that the training area is going to be 0 in a lot of cases. But then doesn't necessarily mean that you have a good prediction model because of this very situation here. Okay. So always a good strategy is to begin with some simple model and then add complexity gradually. Okay. Instead of trying to be a superhero and then just apply some fancy machine learning algorithm and then just hope for everything to turn out good. Okay. Here's another kind of table showing some different situations. Now, instead of only 7 training samples, now we have much larger number of training data. And in case we have a larger number of training data, the accuracy of the linear regression, the polynomial regression model becomes much better. Okay. So in this case, it actually turns out if you have a larger number of training data, then the most appropriate degree of polynomial is actually 5. And 5 is where you get the most accurate result. Okay. So that's kind of a usual scenario of applying machine learning model. Now, before to end, here's the problem that I want you guys to think about. So the conclusion of one takeaway message from today is that a linear regression model can be solved by using this formula over here. So the life is good, right? You have a data table, just represent it as a matrix form, and then compute x transpose x, compute the inverse, and then multiply x transpose. If you use MATLAB, inverse is just a simple function inv. If you use Python, again, it's .inv, right? So the life is simple. You can compute this and then just multiply it, and then you have the regression model. But if you think about it, in terms of computational complexity, we have a D by D matrix, which is x transpose x. And in order to calculate that, we need this much of multiplications and additions. Excuse me. In the meantime, we need to invert this matrix, which is d to the cube of computational complexity. And finally, when you multiply them together, you're going to end up doing this much of multiplications. Okay. Now, if you have a large number of n, obviously this is a problem. Also, in big data problems, you oftentimes end up having a large d, and when d is large, again, that's another problem. So that's a situation we often come across in big data analytics. So the next class, what we're going to do is to talk about some of the strategies to get around the issues of computing this pseudo inverse, and then come up with a better and faster and more efficient algorithm to compute regression. So thank you very much, and I'll see you guys next Tuesday.